Welcome back. So this is the first of a series of 4 videos focusing on the sketching of complex functions. And what I mean by complex functions is looking at the sketches of the addition of 2 functions, the product of 2 functions, and then moving on to the sketching of composite functions. This video we're focusing on the addition or subtraction of 2 functions, and we're going to go through a series of steps to help us to get a sketch. And I'm going to say it's a sketch. You must remember it's not a portrait. So it's just a rough guide as to what the function will look like. But we're going to focus on the steps that we take to get a sketch of such functions. The steps that I'm going to go through really do sort of replicate themselves for the different um, types of functions that we're sketching. So the steps that I'm going to want us to ask or to focus on is firstly writing the function as a single function. That sometimes can give us tips as to what type of function we're dealing with. We're going to then sketch the function in its separate parts, meaning, the 2 functions that we're adding together in this case. And then from the single function, we're going to also inspect its intercepts, if there's any asymptotes, what they may be, and if there's any stationary points, we want to have a look at those. We're going to identify that the stationary points are going to be found by using differential calculus, meaning we're going to be exploring f-x equaling 0. And lastly, once we've got all this information, we're going to then consider the curvature of the graph and try to get a representation of what hx, or the addition of the 2 functions, is going to look like. All right, so we're going to have a look at 2 examples. This is the first one, and it states this: if fx equals x squared and gx equals sine open bracket pi x onto close bracket, sketch hx equals fx plus gx. So my first step that I'm going to do is I'm going to write it as a single function. And with the single function, I'm going to write hx equals x squared plus sine pi x on 2. There's my expression. Now, there's nothing, it does look like a complicated expression. And when we're going to sketch it, we're going to have to look at it in parts. But there's nothing that's coming out from that expression that says, oh, it's going to be a truncus or it's going to be some form of logarithm. We can just see that it's okay, it's a function that we're going to sketch in parts. Then we're going to move to a preliminary sketch. And with our preliminary sketch, what we're going to do here is we're going to sketch fx and gx separately. So I'm just going to put my axes together. There's my y-axis, my x-axis. I'll just call it x and y. And then I'm going to focus on fx. Now, fx, I'm going to use a blue dotted line to sketch fx. And I can see that fx is this term x squared. So I'm going to sketch out a parabolic curve. Okay, looks like that. And then I'm going to focus on sketching gx. So gx I'm going to sketch in green. This is the sketch of sine pi x on 2. I'm going to note here that, look, the period of that sine pi x on 2 is going to equal 4. Therefore, I'm going to split it up like so with such intervals. And then I'm going to start doing the sketch, and I'm just going to have it with an amplitude of 1. Okay. Now, I can tell here, I just neatened this up a little bit. Even though it is just a sketch, I'm going to try to get it a little bit correct. I might want to reconsider my sketch of fx here, just because with fx, that should be going through this point 1, 1. So I'm just going to re-sketch this function of fx. So it's going to look a little bit like the function that we're after. Okay, so there I've got a preliminary sketch. I haven't started sketching what hx is going to be, but I've just gone ahead and I've sketched fx and gx separately. All right, my next part now is to have a look at my points of interest. So I'm going to have a look at my y-intercept. And when I'm discussing my points of interest, I'm talking about the points of interest for hx. So my y-intercept occurs when x equals 0. This in turn means that I'm looking at 0 squared plus sine pi times 0 on 2. Okay, that's 0 plus sine 0, which ends up equaling 0. Okay, so that gives me my y-intercept. I'm then going to consider my x-intercept here. This is when y equals 0, and I'm going to look at 0 equals x squared plus sine pi x on 2. Now there's a little bit of algebra that we may use to solve this. I'm going to skip ahead, and I'm going to say that the x-intercepts are going to occur when x equals -1 and when x equals 0. Okay, that's nice. I'm going to then consider my asymptotes. Now, due to the nature of hx and the nature of fx and gx, there's no discernible asymptotes here. So I'm going to say that there's none. Okay, so no asymptotes. And then I'm going to explore my stationary points. Now, to establish my stationary points, I'm looking at h dash x equaling 0. Okay, this gives us 2 points. I get x equals -0.529 and y equals -0.458, or if I round up, 0.459. This is, I said 2 points, but I really meant just one, just 2 coordinates, or one set of coordinates, and that's what we're looking at. So that's our stationary point there. Given that I've got all this information, I'm going to return to my preliminary sketch. I'm going to pull this together. I'll put it underneath all the information that we've just established. So let's get it looking quite sharp. Okay. And then what we're going to do is we're going to put our y-intercept in here. I'm going to put my x-intercept in here. Okay, so there's my y and x-intercepts. And then I don't have any asymptotes, but however, I do have importantly a stationary point here. And I can safely assume that hx is going to have a region of the graph that looks like that. I'm also going to note here a couple of factors. So I'm going to note that for 2, gx equals 0. So that means that the point of hx should lie on fx. Just remember, hx equals fx plus gx. If I say that hx equals fx plus and gx equals 0, that just leaves me fx. So I'm just noting that that's going to lie on fx. I'm also going to note here that I have a 0 point here. Therefore, that point, okay, there should be some symmetry here. It's just a rough sketch, but we should have that point existing on hx as well, okay? So the 0 points mark up. Now, what I need to be concerned is these two values, or all the values in this region. So what I'm saying is fx is a positive and gx is a positive. Therefore, when I add them together, hx has to be greater than fx. And that means that when I sketch, it has to be not a straight curve. Just get my curving correct. It has to be something of that nature. Okay. Now I'll get rid of that region. When I consider this region here, gx is negative. Therefore, hx has to be less than fx, which would make sense. Likewise, if I consider this region here, gx is less or is negative, that means that hx has to be less than fx. I'm going to get a curve that looks like that. And then in this region here, gx is positive, meaning hx has to be greater than fx. Okay, and there we get a sketch of hx. Now I'll just highlight this so that we can follow. Just remember it's a sketch. Okay, I'm doing it by freehand. It just gives us an idea of what it would look like. Okay, and such is the sketch of hx equaling fx plus gx. All right, so we'll move on to the next example. So example 2 states if fx equals 1x and gx equals e to the x, then sketch hx equal fx plus gx. So like we've been doing prior, I'm going to write my single function, and with my single function, I'm going to write hx is going to equal 1 on x plus e to the x. Okay, now we could rewrite that. We could explore different ways that we could express that function. I'm just going to leave it in that basic term for our purposes. But you could do other things with that and then see if you can get different results. I'm now going to focus on my preliminary sketch. And with my preliminary sketch, put my axes in. I'm going to focus on fx. So I'll just note fx. I'm going to put in blue. Okay, so that's what fx. I'm going to note here that fx has an asymptote fx has an asymptote at x equals 0, going up that way. I'll just denote it that way. And actually, I'll put it through, just dot dot the whole way, just so we know that that asymptote is there. There is also an asymptote at y equals 0, but I'm going to choose not to focus on that at the moment. And then I'm going to also sketch EX as shown in blue. And I'm going to try to sketch this as well as I can. Okay, and EX looks something like so. All right, so there's my preliminary steps. I haven't started sketching HX yet, but I've got HX sketched in parts. I'm now going to have a look at my points of interest. So I'm going to inspect my y-intercept, x equaling 0. I'm going to say this equals 1 on 0 plus e to the 0. I want to note here that 1 on 0 is undefined. Therefore, the whole expression or the whole value of, or the whole idea of having a y-intercept, it's undefined, meaning that it's not going to exist. The x-intercept, we're going to look at when y equals 0, and we're going to explore 1 on x minus in ex. I'm going to work this algebraically. I'm going to come to the realization that this does not give a solution, okay? And if it doesn't give a solution, I'm therefore going to say that it doesn't exist. I'm going to have a look at my asymptotes, okay? I can definitely say here that there's an asymptote at x equals 0, and I'm going to retain that asymptote, okay? That asymptote was taken from this section of hx, and that flows on to the actual sketch of hx. So the asymptotes carry through, and then I'm going to explore my stationary points. So my stationary points, I'm going to be exploring h dash x equaling 0. I get a stationary point at x equals 0.7035 and y equaling 3.442. This gives me a point here at 0.7035, 3.442, which is really interesting and important for me when I'm going to come to my sketch. So now what I'm going to do is I'm going to, at least in this app, I'm going to copy my preliminary sketch. I'm going to then choose to assign some of the values that I found. Okay, so I'm going to first go to my y and x intercepts. I don't have any to show. I'm going to have a look at my asymptotes. I've already got my asymptote written in there. I'm going to have a look at my stationary point. So I know I have a stationary point at 0.7032 and 3.1 or 3.442. So I'm going to put that point in. That's my stationary point. And then I'm going to consider the graph in different sections. Now, considering the graph in all of this section, I can say that both fx and gx are both positive. Therefore, hx needs to be greater than their respective parts. So hx needs to be above fx in this respect, and it needs to be greater than gx in this respect. So we're getting this section of the graph looking like so. Okay, so that's nice. So we'll say here hx equals fx plus gx. And then I'm going to consider my next section. Now, this is really important that we know what's happening in the terms of 1x and in terms of EX, and which one holds more weight. So when I consider this section of the graph, I'm going to note that this part holds more weight. So therefore, hx is going to be a negative value, but it is going to be greater than fx, and we're going to have hx looking like so. Now I'll show it up by highlighting what hx is going to look like. Okay, gives us a highlight of the graph. And then we've got a sketch of hx. That's all for this set of questions and for this video. I hope this helps. Keep on working hard.